Hello students, once again welcome to chemistry classes by Vijay Kumar Sethi. In previous two videos we have discussed about the colligative properties. Now in this video we are going to discuss some more points. First we'll discuss about the abnormal molar mass. Molar mass that is either lower or higher than the accepted or normal value is called abnormal molar mass. For example, normal molar mass of KCl is 74.5 gram per mole. Actually, this is the sum of atomic mass of K and Cl. This will come 74.5 gram per mole. But if measured by using colligative properties, it comes 37.25 gram per mole. Actually, 1 mole of KCl dissociate to give 1 mole each of K plus and Cl minus, that is 2 moles of particles. We are assuming that 100% dissociation is taking place. As we know, colligative properties are directly proportional to the number of particles. Then delta TB or delta TF for KCl will be twice the normal value. And molar mass is inversely proportional to colligative properties. Therefore, molar mass calculated on the basis of this delta TB or delta TF will be half the accepted value. Take one more example. Molecules of ethanoic acid. It is also known as acetic acid. Normal molar mass is 60 gram per mole. Dimerize. What is the meaning of this dimerize? Two molecules will join and form a one molecule in benzene due to hydrogen bonding. See this, the CH3COH. It's two molecule and this will form CH3COH twice one molecule. Now in this structure, hydrogen bonding is shown. This is hydrogen bonding and this is hydrogen bonding. This is one molecule of CH3COOH and this is the another molecule of CH3COOH. In this case, number of particles is reduced to half due to dimerization, and delta TB or delta TF for ethanoic acid will be half of the normal value. As the number of particles reduce, colligative property will also reduced. Therefore, the molar mass calculated on the basis of this delta TB or delta TF will be twice, because molar mass is inversely proportional to the colligative properties. Again, we are assuming that all the molecules dissociate in this. So we can say due to association or due to dissociation, we will get the abnormal molar mass. Now next, Hoff factor, I. This factor was introduced by the scientist Hoff, and this is used to account the extent of dissociation or association. Extent means how much dissociation or association is taking place. And this can be defined by this formula. I is equal to normal molar mass divided by the abnormal molar mass. And I is the observed colligative property divided by calculated colligative property. Now in these two formula, abnormal molar mass is experimentally determined molar mass and calculated colligative properties are obtained by assuming that the non-volatile solute is neither associated nor dissociated. One more formula, I is equal to total number of moles of particles after association or dissociation divided by number of moles of particles before association or dissociation. In case of association, I is always less than 1. See the example of acetic acid. In that acetic acid, two molecules will convert into the one molecule. So we can say after association we will get the 1 and before association we having 2, that is 1 by 2. This is less than 1. In case of dissociation, I is always greater than 1. Again, we have discussed the example of this is potassium chloride, KCl. This will dissociate to give the two particles, that is K plus and Cl minus. Again, if we apply this into the formula, that is number of moles of particles after dissociation. After dissociation, we are having 2 and before dissociation, we are having 1. That's why this will come 2, which is greater than 1. When no association, no dissociation is there, I is equal to 1. For example, value of I for aqueous KCl solution is 2, and while for the value of ethanoic acid benzene, this is 0.5 as we discussed. Now, modified equation for colligative properties after inclusion of Van 't Hoff factor. For relative lowering of vapor pressure, this is relative lowering of vapor pressure, which is equal to x2. But when association or dissociation is taking place, this is multiplied by I. The same case, elevation of boiling point, delta TF is equal to IKBM. Depression of freezing point, delta TF is equal to IKFM. In both the cases, we have put the value of M. That's why our final formula is like this. Osmotic pressure of solution, this is pi is equal to, we multiplied by I W2RT divided by M2V. Now next, degree of dissociation and Van 't Hoff factor. Consider one degree of association and Van 't Hoff factor. Consider one association reaction at equilibrium. That is, reactant is A, and if its N moles are associating and converting into the AN. But again, remember, 100% association is not taking place. And if you assume that fraction of molecules are associating, which is represented by the alpha, that is degree of association. So initially we are having the number of moles is 1, and when there is no reaction, product is 0. If alpha is the degree of dissociation, means out of 1 alpha are dissociated, then we can say at equilibrium the remaining moles of reactant is 1 minus alpha, and for product this will be alpha by N. Now in case of that benzoic acid, when two molecules will combine and form a one molecule, we can say N is equal to 2. Now total number of moles of particles at equilibrium, so this is 1 minus alpha, these are the reactant, plus alpha by N, this is product. And again, if we rearrange this equation and take the common alpha, we will get this one. Now as we know, I is equal to the total number of moles of particles after association and number of moles of particles before association. Put the values, we will get this one. Again, that is I is equal to this 1 minus alpha multiplied by 1 minus 1 by N. Again you rearrange, and finally we can find out that is alpha is equal to 1 minus I divided by 1 minus 1 by N. This gives the relationship between degree of association alpha and Van 't Hoff factor. In the same way, we can find out the degree of dissociation alpha and Van 't Hoff factor. Again, consider one dissociation reaction, that is A is dissociate to give B, and number of particles of B is N. Again, we are assuming that 100% dissociation is not taking place. Only fraction of molecules are dissociate, and this fraction is represented by this alpha, that is degree of dissociation. Initially, A is 1 mole. When no reaction is there, product is 0. If alpha moles are dissociated, then at equilibrium, reactant remains 1 minus alpha and product becomes alpha N. So we can say at equilibrium, total number of particles are 1 minus alpha plus alpha N. Then again, if we rearrange, then take the alpha common, we will get this 1 plus alpha and minus 1. Put the value in the formula of I. Total number of moles of particles after dissociation is 1 plus alpha and minus 1, and before dissociation, that is 1. So we are having this. Then again rearrange. Finally, we will get this one. Alpha is equal to I minus 1 divided by N minus 1. Now, we will discuss some numericals based on this degree of dissociation and association. 2 gram of benzoic acid dissolved in 25 gram of benzene shows a depression in freezing point equal to 1.62 Kelvin. Molar depression constant is given 4.9 Kelvin kilogram per mole. What is the percentage association of acid if it forms a dimer? Dimer means two molecules join and form a one molecule. Now in this case, we have to find out the degree of association. And for this, first we'll find out the Van 't Hoff factor I. we will use the modified equation for colligative properties. Delta TF is equal to IKFM. And if M is W2 into 1000 divided by M2 into W1. Now in this W2, that is mass of solute, is given 2 gram. W1, mass of solvent, is given 25 gram. This is depression in freezing point is given 1.62 Kelvin. Kf is given, and M2 we can find out molar mass of benzoic acid is 122 gram per mole. Put the values, then I is equal to, after putting the values, you will get 0.504. And as we discussed, dimerization is taking place, that's why n is equal to 2. Then by using the relationship between alpha and I, we can find out the value of alpha. This is the formula. Put the value and finally calculate 0.992. This is in fraction. If this is multiplied by 100, then this will in percentage. 99.2% is the degree of association. Now another example, 0.6 ml of acetic acid having density 1.06 gram per ml is dissolved in 1 liter of water. The depression in freezing point observed for this strength of acid was 0.0205 degrees Celsius. Calculate the Vanta factor and dissociation constant Kf is given to you. Now, before we discuss the answer of this question, just see this value of depression on freezing point. This is given in the degree Celsius. But in previous example, it was given in the Kelvin. Any difference between Kelvin and degree Celsius? No. Actually, this is the difference. This is the difference of two temperatures. That's why it may be represented in Kelvin or degree Celsius, but magnitude remains the same. Don't convert this degree Celsius into the Kelvin by adding 273.15. Is that clear? Now see. First, find out the number of moles of acetic acid, and for this, find out mass of acetic acid, which is equal to volume into density. And volume and density is given in the question, 0.06 into 1.06. This will come 0.636 gram. This is mass of acetic acid. Molar mass of acetic acid we can calculate 60 gram per mole. Then we can find out the number of moles of acetic acid. This is the mass of acetic acid divided by molar mass of acetic acid, and put the value. This will come 0.0106. Now we can find out the molality. Number of moles divided by mass of solvent. Number of moles we calculated 0.0106. Now mass of solvent. How this one came? In the question, mass is not given. In the question, that is 1 liter of water is given. And as we know, density of water is 1 gram per centimeter cube. That's why 1 liter is equal to 1 kilogram. So we can say that's why mass of solvent is 1 kilogram. If we solve it, this is the molality 0.0106 m. Again, use the modified equation for colligative property. Delta TF is equal to IKFM. Find out the value of I. Put the value, and this will come 1.04. Now from this I, we will calculate the, that is one half factor we have calculated. I is equal to 1.04. But we have to find out the dissociation constant. And for dissociation constant, we have to calculate the degree of dissociation, and the relationship between degree of dissociation and I is this. Put the value. I is 1.04 minus 1 divided by 2. How this value of n came to? Actually, CH3COH dissociate to give CH3CO minus and H plus. 2 particles are obtaining after dissociation of one molecule of CH3COH. That's why n is equal to 2. And if we put the value and calculate, alpha is 0.04. Now from this alpha, we will find out the dissociation constant of acid, that is Ka. Again, remember class 11th equilibrium chapter. Ka is CH3CO minus multiplied by H plus divided by concentration of CH3COH. Put the value. CH3CO minus is C alpha, H plus is C alpha, and CH3COH is C1 minus alpha. This is from class 11th. C is cancelled by C, we'll get the C alpha square divided by 1 minus alpha. Put the value and calculate, we'll get 1.76 into 10 to the power minus 5. So these are the numericals based on degree of dissociation and association. Thank you.